so I start this, and well, today is the May 8th, end of the World War II, at least in Europe, and I am going to record Lecture 2. Lecture 2 took place face-to-face on February 25th. Nevertheless, during this quarantine period and without these contacts, we had now about 8 to 9 weeks without personal contacts, and I consider this topic substantial and important. In between, some topics were moved to additional topics, so to say, not so important. But this topic here is important, and so I would like to make a record, and you to have a recording of this lecture. Well, after the first lecture, what we found in the first lecture, that we have a flood of information, and human perception and automation are key factors. And what should we aim, and where we should go? We would like to have intuitive, useful, maybe top K, personalized, automated and fast recommendation based on some user preferences, so it should be personalized, each user differently, possibly differently. And so our aim here is to create, well, not to create in the sense of implementation, but rather analyzing and understanding and trying to understand principles. So there will be no coding in this lecture. Well, today in the May 5th we already know this, but and we will more concentrate on a geometrical visual model which can be computed just by drawing tools, and which we hope it is also good for at least some ideas about the user interface. Well, slowly just going through this depiction of slides from the first lecture, well, there is some link to the current state of e-commerce filtering in the first lecture. Then I mentioned some virtual machine. Here is our main motivation. Here I mentioned how this recommendation or customer preferences look today. So here you could choose your areas, so sliders. Here we spoke what happens in some web pages if you make some contradictory requirements, then there is no answer. In some web pages, even if you make contradictory requirements, they say they are sorry, we couldn't offer you any solution, but there is something what is close. Okay, and this closedness is one of the motivation steps. So what is close? In which sense? Close, well, close refers to distance, but we will see that maybe there are also some others. So then we mentioned this recommendation scenario, some competition on Netflix data. Then we mentioned that maybe the goal, whether it is entertainment or something serious or frequency, can play a role. Then we mentioned some heat maps, either it is a gaze or a mouse movement heat map, like here. Then we mentioned also some psychological circumstances. Maybe this recommendation depends on the customer psychology. And today our publication that they are really able to find out your psychological properties. Then about the visualization of data. In psychology, this research was already started before the World War II, and for instance Likert scale, And here I repeat this, that what we are really interested is application layer in this computer hierarchy layer. And so our motivation is to find a system which both computes and both displays the information. Here we say that probably waterfall will be not the right model, even extreme programming not, because there is a customer. What is for us most important is the lean startup methodology, where we don't have a customer, and we are on the side now of the implementation, and we even do not know how. And in this cycle you create the customer, and then you use extreme programming. So here we stress that this will be graphical. And what we said here, well, this is today in expanding topic, that we will use several formalisms. And then I mentioned that there are already some PhD works which will shed light during this lecture. And if you see these slides, you can recognize some slides from later lectures. And then some organization was mentioned. Well, that time nobody thought that this semester will be really organized in a quite different way. Well, so what we can so far say about user or customer preferences? In any case, they are scaled, and they are about ideal values of these objects. So definitely it is a competition. Who will win your be a winner, and you buy the item. In competition in sports, it is clear, because many years, who is faster or can jump higher, it's clear who is the winner, because this is the idea of the sport competition. On the eShop it is not clear, because users are different. Here in sports we agree together on the rules of the game. And of course producers know a lot about this, because there is a marketing segmentation, and then they know that the different segments of market occupied by different persons, maybe demographically or differenced by some other ways, are interested in different kind of products. And in marketing I am not specialist, but I already found that ideal values are somewhere in the head of people. So of course too many items, too many conflict requirements can go. For instance, here you see some interface about cars, here you see some interface about cameras, and if you don't know the market segmentation and the whole offer on the market, then you can very easily come into conflicting requirements and maybe no answer. So there are two bad cases when you go to an e-shop. Either you get no answer, or you get too many answers. And of course, even in the case you have no answers, it would be good to get some clues, so to say. And in any case, in a big number of answers, or even those closed ones, it would be good to have them linearly ordered. So as we are used to perceive the ordering, for instance, from top to down, from left to right, and so on. Okay, so preferential sets will be the main topic, or the main tool we will use to express these preferences. We will see that fuzzy sets were originally intended for linguistic vagueness, so now the preferential sets are the tool. The preference is expressed by some scale. It can be number of stars, or it can be the whole interval 0, 1. And probably, maybe between humans in communication, we can express our preferences in linguistic terms. Something is low, so this is low preferred, this is medium, so this is high, or high value is preferred, sorry. And we assign some degree of preferences. This will be dealt in the lecture 11, I think. So one of our first motivation, except of this web pages where we saw already that some close result can be recommended, is the area of decathlon. So decathlon is an athletic discipline where athletes in 2 days they are going over 10 disciplines. So they start by a 100-meter run, then a long jump, a short high jump, 400-meter. This is hurdles, discus, pole, javelin, and final is a mile. And now if you see, so these are data. Here is a link behind this here. If you see this data, so you see the Scheberle, so his achievements are in green. So, well, definitely he didn't won all disciplines, although he won, well, how much? 5 of them, or 6, 1, 2, 3, 4, 5. 1, 2, 3, 4, well, whatever. There is something, yeah, well, here is the 5th. Okay. So how can you compare this guy and this orange here, which won also some discipline? Maybe he won only 2 of them, but you see in some disciplines he was even better. For instance, here in the 400-meter, or here in this pole. So what we see here, and then we have the third athlete here in color, and then the last one. So the last one was also not the last one in all, even in the 100-meter, probably is a specialist in sprint, so he was on the first position, and somewhere was twice he was the last one, but not always. So what we see, such a comparison, we know what is better. Well, for a run, faster is better. For a jump, a bigger number is better, and so on. So, but what came, because this development of athletic discipline, decathlon, it took about 100 years. So what came as a solution? A solution was make all these achievements commeasurable. So they have a pointing table, and to each achievement there is assigned a number of points, and then the winner is who has the biggest sum of these points. Okay? So, and these points, of course, make this ordering linear. And this is what we would like, because we have also the same situation in our e-shop with our customer. Probably he has interest in many attributes, and now these items in some are better, for instance item 1, and in some other attributes is item 2 better. So how to compare it? Again, it is a partial ordering. And how to make it linear? Well, probably like in decathlon by some pointing function. Okay, so we can now start in the direction of our approach, and what we can see, so there is something like a data cube, okay, we will call it data cube, where there are, for instance, we can depict only 2 dimensions because we are on a paper. So we take the results for 100-meter and for a shot. So what we see that the Scheberle result is somewhere here, and this null, this athlete in this color, or not. Now I think this is the null. So he was quite good, and he is better in all disciplines as compared with this Dvořák, this red one, Dvořák, and this yellow one here, Lobodin. What does it mean better? Well, in the 100-meter run, better means to have a shorter time in which you achieve to run 100 meters. In the shot, better is a bigger distance of your shot. So here is the ideal point in this data cube, so to say. And what we see that this athlete, at least in these 2 disciplines, is really better than these 2. But with this one is not comparable, because this one was better in the 100-meter run, but was not, and this one was better in the shot. Okay. And now, after this point system was introduced, what we can see again, well, more points is better. So now the ideal point is here somewhere. And here are the points which were assigned to these achievements of these athletes. And we see that again, this domination, or that he is better in both disciplines, it remains. So he is still better than both the red one and the yellow one. And the green one is incomparable, because here it has more points in 100-meter, but in the shot he has less. Okay, so this well, motivation, or these observations from these sports, because of course these sports try to be fair. They try to be fair in the sense that the best one, who is the best athlete, but measured by 10 disciplines. Okay. So this will be called data cube, and this is a preference cube, or sometimes it's called Pareto cube. And now, well, there is another depiction, again, same athletes and same colors, but here is the mile run, the last discipline, and here is the long jump. And again, more is the further. Okay, 820 is the ideal here, and in 1500 again the bigger time, the smaller time is better, because you were faster. So the ideal point is somewhere here. Here are against these achievements, and what is here shown, these are athletes which have these achievements same, measured by points, and the points function are here. So before we had this picture separately. So here the data cube and preference cube are separately, but now we put it together, and the data cube and preference cube are put together into one picture. And now this pointing function makes a translation. So for this achievement, I don't know, some 230 centimeters in the long jump, and some 4 minutes 35 seconds. So this is translated here by pointing function for the run, and here is the pointing function for the long jump, and here we are in the two-dimensional but preference cube, where we see some pointing. But in preference cube we already know that this line means that the sum of preferences is the same. This yellow line again indicates that these achievements on this yellow line would be equal. And what we already see, that, well, bigger sum is here in the bottom left corner, so the red one is better. So this we can even visually see that the red athlete, well, restricted to these two disciplines, is better than this orange one. I hope this is the orange one. Okay. So as I said, now the point is that we have put together data cube and preference cube, and we can do the same in an abstract way. So here is an abstract data cube with some abstract domains. We are even not interested in the numerical values here. We assume only these domains are linearly ordered. And here is a preference cube, again same as in decathlon. The only difference is that we probably, because here in the decathlon there is, so to say, one user, one understanding who is the winner. The winner is decided by rules of Athletic Federation. So one point of view of Athletic Federation, well, it changed in times, but now from the 1980 it is fixed, and so we can say about 40 years these competitions are not changing the rules. But here each user can have different rules, and moreover it can look like this, that there is some ideal point and this is less preferred here and less preferred here. So the ideal point is ideal with respect to first attribute and to the second attribute. And then we will have also some aggregation function like here. Again, the ideal point will be here, and we have these parallel representations of items which are of the same preference. Similarly, like in athletics. Okay. So now this is just in formula repeated what I said before. So this International Athletic Association gave rules where there were some pointing functions and the aggregation was by sum, and who had a bigger sum, this was the winner. Now each user has a own pointing function, so to say. Now the pointing function is not going to natural numbers, but we make it easier for us to deal with. It goes to interval 0, 1. And then there is an aggregation function. In generally, this is an aggregation function. And this RFTU is the overall rating, overall preference. So user U, this red one, with this green aggregation function, with this blue attribute preferences on the item. Well, here should be object ID. So here is the error, because we calculate the preference of the object with this object ID. Okay, let's call it E, this object, whatever. Okay, so now we start slowly in this lecture, because it was the second lecture in the semester. We slowly started with understanding this our representation of preferences. Later we will see that it is not just an artificial some model, but it fits also with some other model even from some companies. And so here is written in mathematical formulas. I don't go to read mathematical formulas, but you can, if you read it more carefully, you will see that these are equations of these functions, and again, here are ideal points, and here are some items. Okay, what we see here, that these attribute preferences can have different shape. Maybe there is a ideal interval, not only an ideal point, but maybe some ideal interval can be considered as acceptable for this user. Similarly here in the first attribute, but maybe it can look like this blue one. So he or she prefers these smallest values, or maybe the preference can have this shape. So in the middle is the less preferred, and extreme values are most preferred, like this user, because we see here is 0. 0 means not preferred at all. 1 means most preferred. So this is a 0, 1, and this is the domain. And again here, so we see that this yellow user has ideal points. So ideal points are here in these corners, these yellow corners. But all of this can be translated to the preference cube. And how it is translated to preference cube, it is here described by detailed construction. So we take, but we have made this repetition also in the lecture 8, in this repetition lecture. So I go faster through this, and we can just find this attribute preferences, and then the point here with this coordinates, which are preferences according to first and according to the second. So here is the image of the point B in the preference cube. We already mentioned that such a point can be obtained, at least in the case of these triangular preferences. So it has in 4 cases. So it has 4 co-images. Okay. And well, what we have to also understand here, we are starting to understand which points are comparable and which are not. So B is in all coordinates, because here is the ideal point, and 1 is here and 1 is here. So in both coordinates is better than E. But B is better in the first coordinate than D, but D is better in the second coordinate than B. Okay, so these points are incomparable. So this slide is about the notion of what point B is dominating this red area, and point B is dominated by this yellow area. And for instance, point F is these are images of items in the preference cube, is dominated by this green area, but these 2 points are not comparable, again because B is better in the x1 value and F is better in the x2 value, well, whatever. Now the solution of this incomparability or this partial ordering can be made similarly as in Decathlon. So we choose, well, we restrict to linear functions, we restrict to 2 dimensions, and then we also restrict to pointing function, so to aggregation of pointing function by some linear function. So this red one, you can check that this is true, the function 2x1 plus x2, because if you go here, then if you insert x2 here 1, so you get 1/3, and if you insert here 1/2, then you get again 1/3. So this is a contour line, and these are other parallel representations of higher and higher. So the motivation comes from geography, where we 3-dimensional objects like hills we are representing by contour lines, and we understand geographic maps that this is probably the peak, and here is the hill is more precipitous, and probably if I would like to climb the hill I would like to go this way. Yes, and here we see some contour lines. For instance, 1/3 we already calculated, so 1/2 is this one, and 2/3 is this one, and so this gives a linear ordering, but there can be different users and different ordering. So if I assume that there is a red user and a green user, then for the green user, this F is the best, or F is better than E. But if I go and F is better than C, yes, in this red user. But if I go to the green one, then this is still better because it is dominated. You see, both coordinates are bigger. But here, this C has x2 coordinate better, but E has x1 coordinate better. And now look what happens. What happens? For the green user, C is better, but for the red user, oh, sorry, maybe I could have chosen some other examples. So some orderings which are incomparable, can be made opposite, different. Okay, so I had to think about it a little bit longer. So anyway, what we see here. So here is one of the most important tools for our lecture. So on this diagonal, we can really find the preference degree of a contour line. All contour lines going through this point 1/3 have preference degree 1/3, because if you insert here in these equations the same number, because the points on diagonal have both x1 and x2 same, then you get the same value, and all these lines have the same value as are the coordinates. And more or less, what is also important, that these contour lines with positive weights, because we assume, because our user functions are closed under negation. We already have seen some can have a triangular preference, but some other user can have an opposite. This can be the least preferred, like here. Okay, so our attribute preferences are closed under negation, or 1 minus x in this case, And so we consider only weighted sums with non-negative elements, okay, with non-negative weights, okay, and so we can have contour lines which go through a point, but it should go through this northwest and southeast quadrant. So no contour line in our model can go in this quadrant where the diagonal is, because here in this quadrant are points which are dominated by this point on diagonal, and here in this quadrant are points which are better in both coordinates than this point here, okay? Well, so this idea of these points on the diagonal, and we measure this relative distance of this diagonal here to the total length, and we can say, oh, this point has, and all this contour line has 0.54, and so we can see here, what we see here, again, is some analysis of some situation of some points and some different users with some different aggregations, okay? And again, just as a repetition, so this mathematical formula RFTU of this point E is here, and we have a connection between these mathematical formulas and our graphical depiction. So this is important. Although we will solve our problems only by ruler and by graphical means, we see that this is somehow connected also to mathematical formulas and numerical computation. We will see later. Okay, now there is an important point which these slides show. How can such contour lines, so these are contour lines of one and the same aggregation function, because these are parallel. How can they be depicted in the data cube? Because in the data cube there are items, okay? Of course we can make images of items, but so after a short observation, we can see that, well, this point D intersects this attribute preference in these 2 points, but the second coordinate is 1, so it means it is on this line, and this intersection we go up, and so the contour line, this blue one, dashed line, goes to these 2 points. Moreover, this point here has the x1 preference 1, so it will be on this line, and the second preference degree is here on the attribute preference of the second attribute, and we see it goes through this point. So this dashed line, this geometric area is the area of items which are better than this degree. For instance, we see B is here inside and D is outside. Okay, so it preserves this membership being in the area better than or being in the area less than. Okay. Similarly, we can say also something about the diagonal. So this diagonal has co-images here from the ideal point into these 2, and even these relative distances. So we can see that the relative, and we can also check it numerically, to the total length in all of these 4 quadrants is the same as is the relative distance of this here. Okay? So this is a quite good observation, and now we are slowly more and more familiar with these depictions. Okay, here we still assume we have 2 users, but they have same aggregation, and this already starts to look like some tasks. Well, because what we are expected these 2 images of the point B, and we are expected to depict a 1/2 and 3/4 contour line here in the data cube. But because of these different attribute preferences, so this solid line is has a co-image in these solid lines here, and this dotted line has these co-images. So what we see, that this object B, but this is a green image of the object B, is here in this dotted line, area of the green contour line in the data cube. But the red image of the point B is here, and it is even outside the solid line area, and really here is the red solid line area, and the point B is outside. Okay, so it makes sense to switch between these two data cube and preference cube imaging. Of course, we can now think about possible formulations of tasks. We can have several sorts of attributes. We can have different attribute preferences, same aggregation, same attribute preference, but different aggregation, or everything is different. It depends on the shape of this function, and we have to be able to interpret these results and discuss this. This is slowly going this direction that I hope that your Lean Startup project will use some of these ideas of this visual understanding of which objects and items are preferred more or less. So this slide shows that maybe we can have some areas of data cube of some objects. Maybe this is some market segmentation, and then we can have several different attribute preferences like here. And again, these tasks can be variable and can give different results. For instance, if we have such a situation. Here we can imagine that even the ideal point need not be exactly positioned. Maybe it is somewhere here, because maybe I don't know exactly what is the ideal point of the red user. And the green user can have ideal point like this. Maybe we know these attribute preferences with bigger or smaller value, because you see this is, if here is the ideal point in this left part of this circle, maybe it's here. And then we even can have a different approximation of aggregation function. So maybe the red user has aggregation function somewhere here in this angle, and maybe the green user has aggregation function in this angle, who knows. And this can, we will not go into solving this situation, but this is a motivation that this visualization has further possibilities, and it can be used in several ideas of projects, maybe. Again, what we see here is a trapezoidal degree of preference, and in the next slide, I think, well, maybe not exactly the same, but what you have to see here is a trapezoidal preference, but it is a little bit more general form than in previous slides, where there were triangular preferences starting in the minimum of domain, going to ideal point, and then to maximum of domain. Here some values of domains are not preferred at all, so here is the preference degree 0, okay? Then it goes up, here is the ideal interval, then it again goes down, and here is the totally not preferred area of domain. And same is in the second. But now look, how do these contour lines look like? So these areas where it was 0 preference, and here also 0, so this forms these corners here, okay? Here, the ideal intervals form this rectangle, so this is ideal area in the data cube. And here we have 5 different contour lines. Of course, this is the last preference, and this is the highest preference. And so you have to try to go to this. But why are these lines going here to this area? This is because this point here is smaller, so this point is smaller than this green one here, and so that's why it goes here later to this area. Okay, so this you have to consider this image and try to understand it and try to well, you should be able to repeat it anyway. Again, so here is a catch, of course, that here the smallest value is an interval and the biggest value is an interval. So here in corners are most preferred objects, so we have 4 corners with most preferred objects. And here we have in the middle this rectangle of the least preferred object. So this is the opposite case to this one here. And again, the behavior of these contour lines depends where is this violet contour line and where is this green one. And here this point and this contour line has higher preference degree than this here, and so it decides whether the shapes are like this, or here are this violet is lower and here are this green this higher. Okay, nobody said that these attribute preferences have to be only triangles or trapezoids. This can be also partially linear, but we don't give it to our tasks because it is time consuming to draw, but same principles how we use this preference cube contour line and how we construct these co-images, same principles can be used also here, and then we get such a strange area of a contour line in a data cube. Well, so this was a first lab probably for the first lab, and so it was an example of a task where you were asked to illustrate these images of points, depict the preference cube area dominated by item E and dominating item E. So this is an English grammar difference, so you have to be careful. And depict both in data cube these areas and depict the 3/4 contour line. So this was the task formulation, and here is the solution. Okay, and we discussed it several times, so now I don't go into details. And here is even a little bit more images, and here is also a average preference contour line. Okay, what we showed, okay, so here we already or always considered the situation that there are two users, a green user and a red user, and what does it mean, which items are preferred by the green one and by the red one. Okay, but now we used the same depiction for a group preference. Okay, we can now assume that we have two users, but we would like to find out a group preference. Well, here we change to average contour line, and then we change to equal rights. So both users have the same right. You know, already you know this picture from a 4-dimensional depiction of our preference model, and from a 4-dimensional induction case. But here is the 2-dimensional case. So here this red line is user 1 and the green line is the user 2. But when we take these points, so where is the image, where is our coordinates of the red point D? Well, it's here. And where is the image of the green point D? Well, I go here, then I have to go here, on the green line find the same, and here is the intersection. Okay, so it seems that, and this is the equal rights contour line deciding between these two users, and so the item D is probably the one on which they could agree, and there are no conflicts with some other. Of course, we see that the user, the green user had a better object here, the B. So, but he had to take into account that the B object for the red user was quite low preferred, so this image is really much lower than this image here. Another possibility to understand this two-colored data cube and attribute preferences is to consider that the green one is the correct, whatever we know it, and the red one is computed by our system. And of course we see there is a error, because the true ideal point is here and the computed system thinks the ideal is here. And similarly for the second attribute. Moreover, the system can also compute aggregation function in a different way. So it should be, the correct one should be this one, which gives a bigger preference to the second coordinate, but the system, whatever it is, a computing system, thinks that the first attribute is more important. And now we can, for instance, calculate errors of these estimations, and we can calculate it both in preference cube or in this attribute variables. Okay, so again here is a depiction, again same image, green and red attribute preferences and contour lines, but now we can think about this as two groups of cars. For instance, there are red cars which have the gas engine, and then there are green cars which are electrical driven. Okay, and this fact, and what are maybe these are attributes are price and the power of this car, and maybe depending on the sort of the car, the user can change his or her preferences. So this situation is known as ceteris paribus. So more or less we are in a three-dimensional case, because what we don't see that the gas or electro car are not depicted here. They are differentiated by the color. Okay, so this is another depiction of the same image, or another understanding of the same image. Okay, then we showed some images how such of course, because our system here is only two-dimensional, so there is a certain restriction. If the user is interested in three variables, then his preference or her preference cube is in the three-dimensional cube, and maybe this is the weighted average of the user preference, and then different contour lines take this shape. So contour lines are no more lines, but these are planes. So we can say there are contour planes, and here we made a construction. You have to understand a little bit analytical geometry, and here is the point which says all attribute preference is 1/2, and this is in this contour plane. Okay, here is another depiction. So there are again two different users. You can understand two different stories for each of them. And then there are depicted some contour lines 5, 6, one. No. This is 5, 6, and this is 2/3, and this is 1/2, and this is the green 1/2. And so we see that there are different shapes and different angles, how this goes to the ideal point. Well, the ideal point, of course, is somewhere here, and so three-dimensional case is more time consuming, and but it can give also, in some visualization cases, it can give some more hints. Okay, now this image only shows some attempt how to draw this three-dimensional preference cube into three-dimensional data cube. And here are these attribute preferences. So here is one axis, first attribute, second attribute, and the third attribute. And in all of these attributes we have some attribute preferences. Okay, so and this can again be used to transforming points from data cube to preference cube, or transforming contour lines from preference cube to data cube, and so on and so on. But this is more time consuming. This is just an illustration for you to see that maybe if you in some project, in some lean startup, you would like to implement it, you can also use three-dimensional data, at least, because now the problem is how the users decide what to buy, whether they have two most important attributes or maybe three, okay, or some attributes like this gas driven car or this electro driven car. Maybe some attributes can be modeled by this ceteris paribus again, and so we can have even in this image there can be driven hidden four attributes if the one of them is such a ceteris paribus attribute. Okay, here we dealt with a problem or the question. Well, it is good for understanding this model. Can 2 points change the order switching from the green one to the red one? For instance, think that the green one is a true and the red one is the computed. So can our computation give us opposite ordering? Can our computation and our recommendation change the order? Of course it can. If the ideal points are here and here, so then in the computed, this point E is better, and we can really see it here, the red E. And if in the correct ordering, this F is better. So in this green, okay, here you see this green one, okay, in the green contour line, because here the contour lines also have different shape, okay. But what happens if these ideal points or ideals somehow coincide, or at least are contained one in each other? So we have here an ideal area, an ideal point, and now we have these contour lines of aggregations, and these are attribute preferences. So here we can see a depiction of a phenomenon which will be later also appear in preference learning. What we see that in the green understanding, this item Z is better because this contour line here is closer to the ideal. Okay, so Z is the best, and then Y is less, and the worst from these three is X. Okay. But in the understanding of the red contour lines, these are computed contour lines, and again, what is closer to this ideal area, well, is the point X. So it totally changes this order, okay? So here, of course, here we are depicting only one quadrant of these preferences, and it is also constructed here, okay? What we can also see both here and here, the construction cannot be done in the preference cube because these attribute preference functions change it, the order from the preference cube. So we have to make this construction in the data cube and then to transform it to preference cube and check whether it is really true. Oh, okay, so then there was a question already whether how to deal with categorical data. So for a car, for instance, assume that the second attribute are types of car, and we have hatchback, sedan, SUV, crossover, coupe, convertible. But maybe these preferences are discrete, but maybe we can at least ideally in our case of our depiction consider that they lay on these lines. And maybe again for the gas cars these preferences are different than for the electrically driven. And here can be the price, and for instance we see that, well, probably it should be opposite, that the electrical are more expensive. Okay, these are illustrative examples, but we have to be able to work with this and then to make decisions. For instance, what would be the ideal car and type of the car for the green user? Because now because here there are these categorical data, So the data points can lie only on these lines. So they cannot, even when these functions are triangular, so data, because a car E can be either SUV or one of these six types. It cannot be anything else. Okay, here the price of course is continuous. It can be arbitrary here. So, but it on these horizontal lines there is no choice, only these six possibilities. Okay. Okay, so we go further into these different data types, and this is about books. And here we have some categories of books, and well, I don't go to read this, but it is about this. Okay. And in these books, we already made a research on some benchmark with Ladia Peshka. Here is a link. So in this display mode, when you click to this link, then you can go. And here are for instance, the action, the fiction types, and we can ask for a preference degree, and it can already look like this. So this is something. It starts a feeling for some inductive task that we already know some. For instance, adventure, and here is crime, and here is drama, fairy tale, and romance, and we already know some preferences. So these are 5 stars and 4 stars, and we have, and here are the authors. For instance, Sapkowski for this special user, or Rowling with this adventure, or Karl May, and then we see this crime. So here is Conan Doyle and Christie and Puzo, and here is William Shakespeare, King and Dickens for the drama, and here are Brother Grimm, Andersen and Lang for the fairy tale, and here is Jane Austen, Gabaldon, Bronte, Mitchell for romantic. Okay, so we have here a data cube where here are writers, here are these categories, and here we have objects with the user preferences. So what we can see, the most preferred book read by this user was Jane Austen here. And another depiction, for instance, here we can have a number of books which were read by this user, and here are again these categories, and here is the preference cube by these stars, and what we see that the best object probably is here this drama, because it has quite high number of stars. So here is the projection of stars. And this drama book, there was a lot of drama books read by this user. So probably if he really likes drama books, he or she, and read a lot of them, so probably he or she most prefers these drama books. Okay. Okay, here is another display of some user ratings on IMDb. It's about movies, and this movie Parasite is from South Korea. It won the prize this year, and here we see several different depictions. So probably users are more used to this diagram. So you see the 10-star rating was by 26%, 9-star was the most frequent one, and then 8-star, and then we see that these low ratings were not so much present. We see also the number of votes for this. Then we also see a demographic study about the age and whether males or females. Well, okay. What you can see, of course, there are problems in this data, because some of these female below 18 and males below 18 do not sum up to the total number of below 18. So it's strange, maybe there are some people without specifying sex, but you see that so there are much less females watching this movie. It is, again, you cannot compare this. And probably this arithmetic mean of this rating is not very fair, because there were much more males. So if you look here, it is 4 to 5 times more males watch this movie, and so this rating was most important and influenced the global rating of all these users. Okay, so there are different ways of depicting preferences. Well, here under this ring is hidden a paper, which is quite interesting because it says what you can do with movies. For instance, you can go to IMDb rating, Rotten Tomatoes, and a lot of other servers. And this guy in this paper, so I choose just two paragraphs on this paper. This guy made a bigger analysis, and what he discovered was that probably a normal distribution between these ratings, and more the distribution is by patterns. You can have a look on this, it's interesting. So okay, so we are coming now to the close to the end, and again there can be really different shapes. You can see this user here has such a preference, and here has such a preference. So probably there is a ceteris paribus, because here has a different form of the preference, and here has another different form. Again here the green one, so green one is probably sensitive to prices and to power in such a way that he distinguishes and has quite different preferences depending on these attributes. And the red one has more continuous preferences and even a different shape of the aggregation. So okay, what we can think here about almost arbitrary shape. What we are fixed to are such linear functions. In order, we can easily make images of points that just by these intersections. Okay. Again, a new form of depiction for categorial data. So now a category can be represented by an interval here in domain. So some values from these, say, minimum to maximum are most preferred, and then these are less preferred, and so on. So this categorical data can be also attribute preferences can be depicted in such a way. Okay, so this was a repetition of the session of the lecture 2, which originally found place on the February 25th, and now on the May 8th I made this recording just for you to have this recording in the YouTube, and you can access it. So now I stop the